To calculate the flux of a vector field over a curve, we need a different kind of line integral. You can see it down there in the bottom left, that f dot n ds, that n stands for a normal curve. So instead of calculating the flow along the curve, we're going to kind of calculate the flow along the normal to the curve, and that's going to give us that fluxy bit. Anyway, the way this ends up falling out is this formula here on the right. This m times g prime of t n times f prime of t, and that m and n are the components of the vector field f. And we say along the curve C because we're still going to plug that parameterization in anywhere that we have y's and x's. So let's calculate the flux of this vector field over the circle of radius 2 centered at the origin, counterclockwise orientation. All right, and we know how to parameterize the unit circle. Circle of radius 2, since it's still centered at the origin, we're just going to multiply the components by 2. All right, so if we want to have a circle of radius 2 centered at the origin, we're going to have 2 times cosine t, comma 2 times sine t. And then we know for counterclockwise orientation, we want our t to go from 0 to 2 pi. All right, so the hard thing about these flux integrals are getting the m, n, f, and g all in the right place. So that's what I'm going to label first. All right, so our m and our n are components of the vector field. All right, so this is m, this is n, and then f and g come from your parameterization of your curve. All right, so that's going to be the 2 cosine t and the 2 sine t. All right, so our line integral says to do the curve m times g prime. So m is x minus y. G prime is derivative of 2 sine t is 2 cosine t. Minus, just copying down that formula from the bottom left-hand box, has got a subtraction in between. And we want n, which I have as x plus y, times f prime, which is going to be derivative of 2 cosine, that's negative 2 sine. And all of that's going to be dt. All right, so that integral is currently a mess. It's got mixtures of x's, y's, and t's, but the whole integral is a dt. So this is what that integral with the c at the bottom means. We want to integrate over the curve. So all of the x's and y's need to get replaced by their parameterized value in the r function. Okay, so everywhere I see an x, I'm going to put 2 cosine t. That's the parameterized value of x. So I'm going to have 2 cosine t for x. Y is 2 sine t. All right, and that was just those two guys right there. And then I'm going to multiply that by 2 cosine t. All right, then I've got x plus y, so same idea, 2 cosine t plus 2 sine t. So that was these guys. And then I'm going to multiply by negative 2 sine t. dt. Now everything is t's. It looks like a mess. Hopefully a lot of that's going to cancel out. And we're going to integrate that from 0 to 2 pi. All right, so I need to do some distribution here. I'm going to distribute 2 cosine t and the negative 2 sine t. Just to make my life easier, I think I'm going to cancel out the negative in the middle with the negative on my 2 sine t. That way I don't have to worry about that. But let's do our distribution. So I've got 0 to 2 pi. I'm going to distribute 2 cosine times 2 cosine. That'll give me 4 cosine squared. Then I've got minus 4 sine times cosine. Okay, plus in the middle, get to that second set of parentheses. I'm going to distribute 2 sine to both of those terms. I'm going to get 4 sine times cosine. Plus 2 times 2 gives me 4 sine squared. And this is turning out much better than we could have hoped or imagined. These two terms in the middle disappear entirely. And I got a 4 cosine squared plus a 4 sine squared. We know that's going to simplify with that Pythagorean identity. Let me clear off the slide and get some more room. With those middle two terms gone, all I need to do is factor out the 4. So 0 to 2 pi, I'm going to 4 times cosine squared plus sine squared. I know that that's equal to 1. So I've got 4 times 1 dt. Very easy to integrate, right? Just 4 times t. So we get 4 times t evaluated from 0 to 2 pi. Plug in 2 pi and 0, 4 times 2 pi minus 4 times 0, and we get 8 pi. All right, so there's our flux across this curve. Let's see if this makes sense from the picture. So here's our vector field and our curve drawn in the plane. And it does look like, if we're thinking of this curve as being sort of a net stuck inside our vector field, it does look like a lot of the water, electricity, whatever it is crossing through the curve. So it makes sense that we got a pretty large flux. One more example, so we get the hang of calculating flux of a vector field. So we've got the vector field x squared comma y plus 1 over the curve C, which is the line segment from 0, 0 to 2, 4. All right, so let's just draw a quick graph of this line segment. So we're going to go from 0, 0 at the origin to 2, 4. So 1, 2, 3, 4. And we'll draw that line segment. All right, and that's just a line that has a y-intercept of 0, and it looks like a slope of 2. So we're going to say y equals 2x. And as always, when we have a rectangular equation, the easiest thing to do is to let x equal to t. So I'm going to say that my parameterization is where x is equal to t. And then since y is equal to 2x, y will be equal to 2t. And since x is t, x is going from 0 to 2, and those are going to be my limits on t. So just like the last example, I need to get straight what is m, n, f, and g. So we said that m and n are the components of the vector field. So m is going to be the function x squared, n is going to be the function y plus 1. The f and g come from my parameterization. So f is function t, and g is the function 2t. All right, so let's copy the formula out of the red box. We're going to integrate over the curve. It says to take the function m, which we have labeled as x squared. So I'm going to have x squared times g prime. So g is 2t, g prime is 2. Formula has subtraction in the middle. Next is n, so that's going to be our function y plus 1 from the vector field. And times f prime. F is equal to t, f prime is going to be 1. All right, and then we're going to change this to being an integral over the curve. So everything that's an x is going to get a t. Everything that's a y is going to get a 2t from our parameterization. And we know we're going to integrate from 0 to 2. So x squared, I'm going to my parameterization. I'm going to make that a t squared. Then I've got y plus 1. My y parameterization is 2t. And then times 1 if you still want to write that. And then we'll just simplify a little bit. So I've got integral from 0 to 2, 2t squared, distribute this negative sign, minus 2t minus 1 dt. All right, that's an easy polynomial integral. We're just going to find the antiderivative. So I've got 2 times t cubed over 3 minus 2 times t squared over 2. Antiderivative of 1 is just t. And then all of that's going to be evaluated from 0 to 2. Let's cancel out our 2's here and then just plug and chug. So I've got 2 times 2 cubed over 3 minus 2 squared minus 2. And then polynomial, when we plug in 0 for all those t's, is just going to be a bunch of nothing. And then just some arithmetic. So I've got 2 cubed is 8 times 2 is 16. So this is 16 thirds minus 4 minus 2, 16 thirds minus 6. Get a common denominator. The 6 will be 18 thirds. And we have just enough room for our answer. That's going to be negative 2 thirds. That's it for Flux. See you in class.